Alright guys, so I've got about 15 minutes to do this video, and so I'm going to try to get through as many of these class problems as we can. So the first question here, though, we finished question number 1 in class, I think. So we're going to start with question number 2 here. And question number 2 is talking about tires, and we've got an equilateral triangle that is 3.72 meters long on a side. So that is an equilateral triangle, which means this angle is 60 and this is 3.72 meters. And it says that we've got positive charges, equal positive charges at either of these vertexes, and then we have a charge, an electric field at the top. So we want to find the electric field at the top, and that electric field strength at the top, and that is going to be in the y direction, is going to be 0.145 newtons per coulomb. So what are we going to do? Well, the first thing is we have to figure out what this force is actually doing. And so the way we do that is we have to be sure that we're drawing this force right. So if we were to draw this point here, all right, and that's where we're measuring our electric field. We have an electric field coming from Q1, and that electric field from Q1 is coming this way, and that electric field at Q2 is coming from this way. And so you can see those are the triangles here, the bottoms of the triangle, and our resultant between these two, and this angle is actually 60 degrees, is going to be coming straight up like this. And so this is our E in the y direction. Now, our E net in the x direction, so each one of these is being broken down into an x direction as well as a y direction. And so the sum of the y's is equal to this one, and the sum of the x's, the electric field in the x direction, is 0. So the sum of the electric field in the x direction is 0, so we would just want to find this y. And so we're trying to find the q's that are down here. And so the way we do that is we actually have to figure out what this value right here is. And the easiest way to do that is to remember that this is a 60-degree angle. Because we've got this equilateral triangle, all of our angles here are going to be 60 degrees. And so if this is our y, then we know that this is a 30-degree angle. We know what this is going to be because we have to we can actually find that. And so if the sum of the y's here is the total of these two y's here and here, then we know that y of q1 is equal to 1/2 of E in the y direction. So our y of q1 is equal to 1/2 of 0.145 newtons per coulomb, which means that y of q1 is equal to 0.725, and that's 0.725 newtons per coulomb. And so now we can actually use this y value to calculate our q. And so the way we have to do that, we have to actually find this resultant right here. And so what we can do is we can use our trig rules, and so we have to use our sine. And so our sine is our opposite over our hypotenuse, and so we end up taking this number and we say that our E of q1 is equal to the y of q1, which is 0.0725 newtons per coulomb, divided by the sine of 60, which gives us 0.0837 newtons per coulomb. And then we can take that number right there, and that's this value in this direction. We can actually use that to find this charge. We know the distance, we know this charge, we know that value of the field. So we say that if our electric field is equal to K times Q divided by R squared, we solve for R, or actually we solve for Q. So we say that Q is equal to E1 times r squared divided by k. That gives us 0.0837 newtons per coulomb times 3.72 squared divided by our 9e to the ninth, and that gives us 1.29 times 10 to the negative 10th coulombs of charge. Sig figs, we've got 3 in the question, so that means that we are 3 sig figs down here at the bottom. So that is question number 1. All right, question number 2 about a fountain in Fountain Hills, Arizona. So we've got a water going 90 meters high, 190 meters high, and we've got it going 120 meters over this way. And so we've got a Q up here, we've got a Q down here, and we've got our electric field over here. And so we're measuring the field, and this is in the x direction, and that is 1.60 times 10 to the negative 2 newtons per coulomb. And we know that this Q is 12 nanocoulombs. We know that this Q up here is our question. So we want to know what this charge value is. So what we can do is we're going to have to find out what the x direction is here. So we're going to have to find out what that is. So this x direction we find with Pythagorean theorem. We actually find that it's r is equal to 225 meters, and it's about that. And so what we want to do is we want to find out what the e to the x of q1 is. What the e to the x of q1 is. So let's do that first. If it's going to be k times q over the r squared. So that ends up being our k times 12 nanocoulombs divided by 120 squared, and that gives us 7.5 times 10 to the negative 3 newtons per coulomb. And that is in the x direction, because Q1 to the field is in the x direction only. So we've got that EX the 2. If this is the total E in the x, then EX to the 2 for Q2 is going to be whatever this is minus this one. And so we end up saying that that's EX minus EX of Q1. And so that ends up being 8.5 times 10 to the negative third. Alright, and so that means that we can actually use trigonometry to find our answer. So we've got this distance here, we need to find this angle, and we use trig rules to find this angle, and we can actually say that that is 57.7 degrees, which means that to solve, let's use a different color now, to solve for our vectors, to solve for this vector right here, the electric field on that, we have to take our E in the x direction of Q2 divided by the cosine of 57.7, and the electric field is equal to 1.6 times 10 to the negative 2 newtons per coulomb. And then we can get our final answer that Q2 is equal to our electric field times our radius squared divided by our K, which gives us a point of 8.9 times 10 to the negative 8th coulombs. And that is that final answer. We've got 2 sig figs from the 12 nanocoulombs, so that means 2 sig figs in our answer right there. Number 4. I think I went the wrong way. There we go. We've got the Pontiac Silverdome in Detroit, Michigan. We've got a charge of 18 microcoulombs is placed on one end. It's actually not micro here, it's milli. If you had searched an answer out online to try to figure this one out, it was from the book in microcoulombs, but now when I transferred it over, it's in millicoulombs. So we're going to treat it like it's millicoulombs. So let's look at this. We've got 2 charges. We've got a charge over here, and we've got a charge over here, and we're measuring the E in the middle. And so Q1 is 18 millicoulombs, and Q2 is negative 12 millicoulombs. They are both going to be moving, or have their field coming in. The positive away from the positive, the negative is coming, actually it's all coming towards the negative, sorry. It's going to be coming in this way. And so our electric field is actually this direction, and it tells us that it's 22.3 newtons per coulomb. And so our negative just gives us that direction, and that tells us that it's the same direction here, which means that we have to solve for the total charge here. And because our charge is all in the same direction, to find this field, the fields are going the same direction, we can actually add up the charges. The charges are additive. So the charges add. So that tells us that our electric field of 1 and 2 is equal to K times Q1 plus Q2 divided by the radius squared, and we want to find the radius. So what we're going to do is we're going to actually then plug those numbers in. So if we know that R is going to be equal to the square root of K times Q1 plus Q2 divided by our E1 and 2, then we can solve that, and we end up saying that this is the square root of 9 e to the 9th times 18 millicoulombs plus 12 millicoulombs, and then divide that total value by 22.3 newtons per coulomb. And we end up solving that this is 3.48 times 10 to the 3rd meters. Now, like I said, this is not actually millicoulombs. It should have been microcoulombs, which puts it more like 100 meters, which is about the same size as a stadium. This is not a 3-kilometer stadium.